So lesson 9B, we want to look at test of hypothesis. For statistical inference, there are two types of questions that often come to mind. The first question is, what is our best estimate for the population parameter? So we want to know the population variance, the population standard deviation. We want to look at the population. We want to look at the population mean. I think I have to. Please, can you mute yourself so that you don't disturb the class? Then when you want to talk, then you can unmute yourself. Okay, thank you. So our interest is what is the best estimate for the population parameter and how good is the estimate. So when we talk of the population parameters, we are talking of the population standard deviations, population variance, but most importantly, population mean. And the second question is, can we conclude that something is true of a population parameter? And how sure are we? Are we really sure? So to address the first question, in the last class, we learned how to construct confidence interval for the population estimates with known probabilities of being correct. In fact, we stopped the lecture at looking at probabilities of 0.95, 0.99, 0.90, and we try to estimate the confidence interval. So today we want to address the second question, which is, can we conclude that something is true of a population parameter, and how sure are we? So we really want to answer that question. And to begin with, we are going to look at the types of statistical errors that is possible anytime we are dealing with hypothesis testing. There are two types of error. We have type 1 and type 2 error. So in statistical test theory, the notion of statistical error is an integral part of hypothesis testing. The statistical tests require unambiguous statements of the null hypothesis. For example, if we say, okay, the firm is not profitable, there's nothing ambiguous about that one. That is an example of a null hypothesis. Then the alternative for that one will definitely be the firm is profitable. So the result of the test of the null hypothesis will not be rejected. In that wise, we say it is not profitable. Or it may be rejected, and in that wise, we say it is profitable. If the result of the test corresponds with reality, and when we are talking of corresponding with reality, then we are talking of a situation whereby we reject the null hypothesis. That is, our alternative hypothesis stands. Then a correct decision has been made. In the example that I'm trying to use to illustrate, it means the firm is profitable and it is accepted as profitable. But if the test does not correspond with reality, then which means we cannot reject the null hypothesis. In that wise, we are saying the firm is not profitable. Then to be able to make that kind of assertion, we are face to face with two types of error that we have to manage. And these are statistical theory. So the first one is type 1 error. So type 1 error is, another word for type 1 errors is false positive. That is the error of rejecting the null hypothesis where it is actually true. Or in other words, the error of accepting the alternative hypothesis, that is our real hypothesis of interest, where the result can be attributed to chance. So in a plain language, it occurs when we're observing a difference, when in truth there is none. And at the heart of type 1 error is that we don't want to make an unwanted hypothesis. So we exercise a lot of care by minimizing the chance of its occurrence. So we are trying to minimize the chance of rejecting a null hypothesis in situation whereby it may be true. So traditionally, we try to set our type 1 error to 0.05. And that is what we are doing. This is what is generally called the level of significance. I'm just telling you where this thing comes from. I know it's possible you have done it before, but it's good to remind ourselves. So when we say our p-value is 0.05, for instance, we are saying there is only 5 in 100 chance that the variation that we are seeing is due to chance. That is what we are trying to say. And the lower the level, the better. So for instance, if you are considering 0.01, it's better than using 0.05. And in several studies, we try to say, okay, don't ever exceed 0.1. So if you read some articles, you will see that sometimes they graduate it from 0.01, 0.05, and 0.1. We don't normally exceed the case of 10% in most cases. So that we are saying we are 90% confident that our result is meaningful. So type 2 error is called false negative. False negative. This is the error of not rejecting a null hypothesis when the alternative hypothesis is the true state of nature. In other words, this is error of failing to accept the alternative hypothesis when we don't have adequate power. So in the plain language, it occurs when we are trying to, when we fail to observe the difference, when in truth there is one. So, and we have to manage the two types of errors. So this is the summary of type 1 and type 2 error, which I've tried to present in this table. Just repeating myself. When I talk of type 1 error, then you are talking of false positive. You are talking of type 2 error, then you are talking of false negative. So try to understand it and the essence, because this is just trying to tell you the essence of our level of significance that we normally allow when we are conducting hypothesis testing. Another word that we normally come across is the null and alternative hypothesis. Let me illustrate the concept by giving us this example. Let us assume that a person claims that 60% of Emaswati are poor. No, this is nothing but a conjectural statement. Please, can you mute yourself? You are disturbing. Someone is disturbing the class. Mute yourself, please. Please mute yourself. Who is the person? Someone is disturbing the class. And it should be part of people that came late. Okay. I think that's better. So let us assume that a person claimed that 60% of Emaswati are poor. No, this is a conjectural statement about the population. It may be true and it may be false. So this type of a claim can be tested. And because it could be tested, it is called null hypothesis. So hypothesis generally is a conjectural statement. So the alternative hypothesis is what we believe if we succeed in rejecting the null hypothesis. And it could be two-tailed, it could be one-tailed. Let's consider this, our typical example. Consider the opinion of the proportion of poor people in Emaswati. Then the hypothesis we follow, we are trying to test the hypothesis of this claim that 60% of the population are poor. In that wise, we say, okay, the proportion, that is what I represent by pi x, is equal to 0.60. And in a case of two-tailed mean that it could be above, it could be below. So in that wise, we say it's not equal to that 0.60. So the alternative will just be it's not equal to. That is a situation of two-tailed test. But if it's one tail, definitely it's either less or greater than. After setting the hypothesis, the next thing is to decide on the probability, just like what I said, that we are willing to accept of making type 1 error. So traditionally, people just say, okay, that's a conventional standard, assume probability of 0.05. So choosing alpha equals 0.05 is very much equivalent to choosing a 95% level of confidence in what we are trying to do. So the third step now will be when you set your hypothesis, when you decide on the probability that you want to use, then the next thing will be to collect preliminary data. Preliminary data. So the next step after setting the hypothesis is to collect preliminary data. Let's go back to our example. So suppose that we now choose a random sample of 200 Emaswati, and we now discover that just 100 out of those 200 are poor, which means the proportion is 0.5 and not 0.6 as claimed by that person. The point here is that is the proportion so far from 0.6 that we can now conclude that the proportion must not be 0.6. And this is exactly what we are trying to do most of the time when we are trying to carry out some of these tests and assuming certain level of probability. So to decide, we need to calculate our Z. So the Z-score is a way of counting the number of standard deviation between a given data value and the mean of that data set. And the formula is very straightforward. It's just the difference between the actual value and the mean, then divided by the standard error. Because the standard error now will be the standard deviation divided by the number of observations. So let's look at a typical example. Let's say the mean yield of maize farmers in Lubombo is 1.5 tons per hectare, and the standard error is 0.5. We know the standard error, we know the mean. And the yield of one of the farmers, let's say, was 2.5. We can compute and interpret the Z-score for that person's yield. So the hypothesis to be tested would be that the mean is 1.5, and the alternative would be it's not, because it's a kind of two-tailed test. So to calculate the Z-test for that particular person, we subtract the mean from the value and divide by the standard error, and we now have to. In terms of interpretation, the Z-score gives the number of standard deviation above or below the mean. So the results show that the value, like in our own situation, the value of 2.5 is 2 standard deviation above the mean. That is how to interpret it. So this decision is however valid if and only if the Z-score is greater than 1.96. So when you have calculated your Z-score, the Z-score that you have calculated, you are not too sure that okay, it is still valid or not valid. So you have to look at the Z table. That is what is normally done before, but thank God for all this computer software. Now we don't need to go too far. Because if you look at the Z value when you assume 0.95 level of confidence or significant level of a p-value of 0.05, then the value is 1.96. So then you now compare this 1.96. Anytime the value is less than what you have calculated, definitely you reject the null hypothesis, which is the case in our typical example here. This is calculating it manually now. But that is a situation whereby we know the population standard deviation, we know the population mean. But most of the time, we hardly know the population standard deviation. So if we don't know the population standard deviation, what do? We still test the null hypothesis. But this time around, we try to take a sample and compute the mean. But we cannot calculate the standard error because we don't know the population standard deviation. We can only estimate it using the sample standard deviation that we have. So in that wise, we can't use z-test. So we use what is called t-test. That is what we use most of the time in our studies. So the null hypothesis in this situation is tested with t-test. And our t-test also is the difference between the population mean and the sample mean. But now we now use the sample standard deviation divided by the square root of the number of observations to calculate our t-value. I believe you're supposed to have done all these things even at elementary statistics level. So where I'm going is, how can you use software to help you out? Because nowadays, I think most of the things we do, there are two things I'm teaching here. Number one, for you to remind you of some of these hypothesis testing, but more importantly, how you are going to use software to undo them. And basically, you must know how to interpret. Those are the key issues here. So when you talk of one sample Z test using R. But before we continue, I want you to understand that Z test is one of the most useless tests in statistics because we hardly use it. We don't use it in real life. It is only when we are teaching like this that we are telling you that it's always the starting point to introduce the concept of t-test. Because mostly we normally use t-test most of the time. We hardly use z-test for anything. But it's always the starting point. In a situation whereby you are certain of population deviation, you are sure of the population mean, then you can now compare your values using the z-test. So in case of one sample z-test, to fix the idea behind z-test using R, we are going to consider an example. I will stop sharing, then I will take you through. When it comes to practical, I will try as much as possible to explain in details so that at least when you are on your own, you can practice it, you can understand it, you can interpret it, you can form your own data set and so on and so forth. So to fix idea behind the z-test using R, we are going to consider the maize price data sets. I have that data set in the folder, which I'm going to use as my directory. I'm going to take us there now. And it is a data set, very interesting data set, prices of 1 kilogram roasted maize cob from 20 roadside sellers, roadside maize sellers in Eswatini here. So let me stop this sharing then and take us to R. So let me share the R, and I will take us through the procedure. So let me show us the data sets so that you look at the data sets fully. You know, usually the starting point is we set our directory, come to session, set your working directory, choose directory. Your directory is where you have all those information, your data set, your code, sort of things. So I have it in my start icon. It's a folder on my desktop. So, all right. So I come to file here. Then I look for the data set. I call it maize price. Maize price. So this is the data set, maize price. So I click on this maize price here. I import my data set. Okay. So it's retrieving the data set now. So let's wait a bit. Okay, that's right. So I import it. That's good. So I've imported it. So okay, let me show us the data set so that you see this data set maize price for 20 respondents. Yeah, so these are the price of roasted maize cob along by 20 roadside sellers in Eswatini. That's Malangen, say 50, 60, and so on and so forth. So the starting point is, number one, you have to check for normality of this particular data set. Because one of the basic assumptions of Z-test is that the data must be normal. So to do that, we need a package. It is called R Companion. R Companion, that is what you need. So if you have installed it and you have library R Companion, it's going to help you to draw the histogram with overlaid normal curve. So to do that, we have plot normal is there. Plot normal histogram, then maize price dollar. This is, this is the name of the variable on the data set. So then the color, you can choose any color you like. I've decided to choose color white. You can choose black, blue, whichever. Then I label my x-axis as maize price in Malangeni. So I try to do that. So let us run it. Run. All right, let's see. This is our plot. So let me zoom it so that we can see it clearly. Yeah, so this is our plot. Yeah. So, and you can copy the image and save it in Word or wherever you want to save it. So that is how to look at the data sets in terms of the skewness of the data set. But looking at this data, you see, we cannot actually conclude easily. It's a bit difficult. because of the shape we have, so we still have to continue to calculate our z-score. So if you want to calculate your z-score, you will need what is called DEX-tools package. We normally use this is descriptive statistics tools package. So if you don't have it, you install it. So let's run this. And to get the z-score now, say it's z-test. This is our variable, base price, dollar miss. Then look at what is happening here. The population mean is MU, and in the question is 67.5. The population standard deviation is assumed to be 9.5 in the question. So that is it. So if you have those ones, then you can calculate your z-score. So you can just run it now and get your result. So fine. So let's look at the results together. So this is a kind of one sample z-test. So our z is 2.2596. And our population deviation is 9.5. Our p-value is 0.02, which is definitely less than 0.05, which means we have to reject the null hypothesis. What is our hypothesis? Our hypothesis is whether the true mean is not equal to 67.5. So but that's alternative. So we are testing the hypothesis that our HO equals to 67.5. That is, we're trying to look at this mean. The mean of our data set is actually 72.3. We can see it here. We want to find out whether this mean is actually different from this 67.5, or the difference is due to chance. So in this wise, we can conclude that the difference is not due to chance because we actually reject the null hypothesis. So there is actual difference between the sample mean and the population mean. So that is what we are trying to achieve here. So I think it's very, very clear, very straightforward. And we are going to go back to the other slides. So let's go back to our PowerPoint show. So that is that about one sample z-test. So by way of going through the example again, let us assume that the average price of 1 kilogram mixed crop in Eswatini is 67.5. The standard deviation is 9.5. The question of interest here is to test whether the sample average price is equivalent to the population mean, or the difference is due to chance. So the first step is to check that the data is normally distributed. And we try to do this by plotting the histogram overlaid with normal curve. And this is the R code, which I've just shown us. And this is the histogram overlaid with normal curve that we have just considered. And this is the output which I was trying to explain here. So it's very straightforward. So there are three basic assumptions when we are dealing with z-test. The first one is the population is assumed to have a normal distribution. The second one is the observation that the data are not correlated. This is difficult to test anyway. And number three, the population standard deviation is known. This is very, very important. In case the population standard is not known, then the appropriate test is t-test. If you don't know the population standard deviation, then you have to use t-test. You have now seen the reason why we normally use t-test. T-test is what we use most of the time, because most of the time we are not actually sure of the population standard deviation before we embark on any of the studies. So that takes us to one sample t-test using R. Like z-test, the basic idea behind the t-test is to use statistics to evaluate null and alternative hypotheses. The t-test is commonly used with small sample sizes, most of the time less than 30. So like z-test, to perform a t-test, we need to assume normality of the data. And the basic syntax for our t-test is t.test, then our data sets. Then we look at alternative. The alternative could be two-sided. If you pick two-sided, which is the default, that is a situation whereby you are dealing with two t-tests. But if it's one t, then it could be less or greater. This is our population mean. And very soon we will see the reason why we have paired and all sorts of things when we are dealing with two sample testing. So t-test for one sample. So let us assume that we have no idea of the population standard deviation in respect of our maize price data. So let's say we don't know it. If we don't know it, we can't be defining it. So if you don't know it, the only thing we can define is the population mean, which is 67.5. Then we now assume the confidence level. So, and confidence level is 0.95 if your level of significance is 0.05. That is, if the type 1 error that you assume is about 0.05, then that wise, just put the confidence level there. Then you run it. So let's see how it works. Let me stop this, then I'll take us to, yeah, let's come back here. The R Studio. So for one sample size, no, one sample t-test. So it's t.test. So we have maize underscore price dollar maize price, comma. So our MU equals 67.5, but that is our population mean, comma. We don't know the population standard deviation, so we just say conf dot level equals, so let's assume 0.95. I want to see what I'm typing, so let me cut this to another level. So run. Yeah. So this is the results. So let's go back to that you see the result clearly. Stop the sharing and return to our slide. Yeah, so this is what we are trying to say. So we have the t is 2.2547. Now we can see that the p-value is 0.03, which is less than 0.05. So in that wise, we reject the null hypothesis. So which means we confirm that 72.3 is actually different from 67.5 at 95% confidence interval. So that's very straightforward to interpret. Let's move forward to look at a situation whereby you have two sample t-tests. Two sample t-tests. So when you're talking of two sample t-tests, you can have is two types. We have two sample t-tests for unpaired sample. That is, they are independent, completely independent. So the appropriate data for situation whereby the two samples are unpaired are one, it should be, you need two sample data. Let's say you are talking of male, female. You may say adopt, not adopt, yes, no, class A, class B. It could be indigene, non-indigene. Just trying to create examples so that you understand the kind of sample we are talking about. So most of the time when you are making comparison of two independent samples, then you talk of two sample unpaired t-test. That's a typical example, a parametric method. So you can be thinking of various things that relate to what we normally do. We may be comparing one country to another country, but it does be true. We may be looking at two regions. Let's say you are comparing Mancini, Bandani. You may be comparing two systems and so on. So get it right. Then the dependent variable must be interval or ratio, so it's kind of continuous data. And the independent variable is a factor with two levels. That's what I've been trying to emphasize. It must not be more than two levels. It must just be two groups. Just two groups. Yeah, so when you have two groups, then the method can be applied. Then usually the data for each population should be normally distributed. So for students, t-test, the two samples need to have the same variance. However, if you want to use wedge t-test, which is the default in R, then the variance may not be the same, which is the standard one, because most of the time the variances are always different. Another assumption, observation between groups are independent. That is, they are not paired, they are not repeated measure data. Then in this kind of example, moderate skewness is permitted if the data distribution is unimodal, in case you don't have outliers. So the null hypothesis is that the means of the population from which the data was sampled for each group are equal. That is, mean of group A is equal to mean of group B. That is what we are trying to look at here. Take, for instance, we are looking at adoption of certain technology. Maybe you are looking at maybe gender differences in the adoption. You want to find out whether male or female adopt, which one is better. So let's say you may want to look at the age differences. You may look at, in which case you may classify them into male and female. let's say you are looking at age differences of the adopter themselves. So you say, okay, we have age of female adopter, age of male adopter, then you can compare. Look at you calculate the t values. You may be looking at, I'm just trying to figure out and fix some examples here and there. Let's say government try to subsidize, and you are looking at maybe the effect of the subsidy on two sets of people, two sets of firms, maybe small firms, medium-sized firms. Yeah, so you can compare. This is the kind of thing we're talking about. So you look at the mean of this, the mean of that, then you compare and see whether there's a difference. And the interpretation is very straightforward. So reporting the significant result as mean of variable Y for group A was different than that for group B. That is the way to report interpret the results. So in terms of the formula, if the variances are the same, we want to calculate it manually now. So this is it. You get the difference between the means of the two groups. Then you calculate, since the variance is the same, that is the variance there, the square root of the variance, then 1 over the number of observations for group A, you square that, then 1 over the number of observations for the second group, then you square. So, and in case you want to calculate, this is how to get the standard deviation of the calculation. But we are not doing it manually, so there's no need to worry ourselves about that. But in case the two sample, the unpaired t-test, in case we have unequal variance, which is the case most of the time, then you have to calculate the variance for group 1, variance for group B, then you get their difference, then you know the number of observations, then you apply this formula. So let's look at a typical example. So we already have our if data. So using if data, XLS data set, compare the mean household size of male and female respondents using t-test. This is a typical example of what I'm trying to say. So if you want to do that, the starting point is to generate two data sets, one for male, one for female, because we must first test for normality assumptions by plotting the histogram overlay with normal curve to share the normality before you now proceed to some other things. So we are going to look at that. So let me stop the sharing, and we are going to now go straight to the RStudio stuff. Okay. So the starting point here is to create male and female data sets in order to check for the normality of the variable. This is the reason why we need tidyverse. Already familiar, I think we'll be using this so that we can manipulate our data and create whatever we want to create. So let's say we want to create male data. This is male data. I call it male data. I'm getting it from if data. This is if data. This is a pipe operator. Filter. The only thing I need to form this data is my sex equals to M. M is for male in sex for the data set. Then for female, sex is F. So I filter them. I create two data sets. Why am I doing that? Because I want to plot the histogram. So let me plot that for male. The household size for male. So on it. Yeah. So let me zoom it so that you can see it clearly. Why is it not showing? Okay, maybe because of the slide. But this is it. Then you do that for female. On it. Yeah, you can see the difference. To do the t-test is very straightforward. The t-test is t.test, household size as a function of sex, data equals to the name of your data set. And you run it. Wait, so this is it. So in order to, so let's go back to our slide for better interpretation, what we are trying to do. So this is, okay. So this is what I've tried to do, to create the male and female data set and check for normality. You have your male data. I call it male data. I'm getting it from HIP data. This is our pipe operator. And I filter male from sex. Here I filter female from sex. I plot my histogram valid with normal curve for male, plot it for female. So done it correctly. This is what I was showing you at that time. So this is the curve. And again, this is the curve for female. So, and if you want to do the t-test, it's very straightforward, just as I illustrated. And this is the results. So you now look at this, you see that your T here is 1.778. You check the p-value. This p-value is already greater than 0.05. And in this case, it means you cannot reject the null hypothesis at 5% level. Since you cannot reject it as 5%, remember, you assume at 5% confidence level. The moment you cannot reject it, it means the mean of group, you know, the mean for female, the mean for male. Yes, you are looking at it facially that it looks like a difference, but you cannot report it. The difference most likely is attributed to chance. That's what you say. So there is no difference between the mean. So it's clear. So that's the way to make the reports. I hope it's very, very clear to us. Yeah. So I will now explain the last aspect of what I think we need to cover today, and explain a few things to us, then allow us to go and practice, because it's an opportunity when you schedule today. It's good to use the remaining maybe hours or whatever to look at it carefully, practice it, and be sure that you yourself can do it using several examples. So I say that you can have two sample unpaired t-test, or you can equally have two sample paired t-test. You have to understand the difference between two sample paired and two sample unpaired. The paired sample t-test is sometimes called the dependent sample t-test. It's a statistical procedure normally used to determine whether the mean difference between two sets of observations is 0. The paired sample t-test is used to compare the means between two related groups of samples. In this case, you have two values for the same samples. In a paired sample t-test, each subject or entity is measured twice, resulting in pairs of observation. Common application of the paired sample test is t-test include case control studies or repeated measure designs. I'll give us maybe 2 or 3 examples so that you fully understand it. Recently, for instance, I'll give an example that we help you to fully, at least to remind you of the difference. Recently, the government increased the price of petrol. So they increased the price of petrol. So definitely is going to have certain effects on the people. It's going to have effects on maybe the transport costs. Let's take transport cost as a variable. Look at it now, why it is called paired sample t-test. We pick just one variable, transport cost. So for that transport cost, we have transport cost before the policy, then you have transport cost after the policy. Don't forget that one. So you have, this is a typical example of paired sample t-test. Is the same, now transport cost, but because of a policy change, you can say before and after, but it's the same. So that is why it is paired sample t-test. Another example, suppose you are interested in evaluating the effectiveness of a company training program. One approach you might consider would be to measure the performance of sample of employees before and after completing the program. So this is a typical example of paired sample t-test. You too, you can formulate several examples and so on and so forth. For instance, I can use my own life as a typical example for you. Before I came to Eswatini, for instance, there are certain series of food that I used to eat. But on getting here, those food are not even available. So I can have a list of all those kind of items and their prices. Then now the change. So when you can have, but I am still the same sample. It's not 2 samples here. So it's paired. I can have before and after. So that is where we normally apply it, particularly as it applies to us in applied economics. What are the assumptions of paired two-sample t-test? The paired sample t-test has 4 main assumptions. Like before, the dependent variable must be continuous, it's an interval ratio. The observations are independent of one another. The dependent variable should be approximately normally distributed. Then the dependent variable should not contain any outliers, in which case you have to test some of these things before you do your t-test. So the formula is very straightforward. The t-test statistics value can be calculated using the formula T equals to M divided by S slash square root of N. M is the mean differences, N is the sample size, and S is the standard deviation. And so let's quickly look at a typical example. Let's look at an example here. So let's come to our R. So there is a data set. I call it small firm. Let us import the data, and I'm going to show you how the data look like before we now begin to work around it. I call it small firm. So this is the small firm. Import data sets. It's retrieving the data. Okay. Import. Now you can see we have the income. Let's say we are looking at small scale firms, and let's say there is a policy that affects them. So in which case we have before and after the policy. Let's take, for instance, the rule of tax. It's possible that potential the government may just say, okay, because of COVID-19, they're actually increasing the tax to be paid by small-scale farmers as small-scale firms. This in order to cushion the negative effect of COVID-19 on the economy. So let's say you are paying, maybe it's increased by something like 10%. Definitely is going to have effect on the income. It could be the other way around anyway. It could be that, okay, oh, now people are crying, a lot of issues. So let us give you tax relief for the next 3 or 4 months because of COVID-19. In which case, if that happens, then the income will shoot up. So, which means the income is likely to shoot up even higher than even before COVID-19, sort of. So this is a kind of typical example. So in this wise, we have the group, we have the income before, then we have the income after the policy. So this is a typical example of what we are talking about. So what you need to do is you have to create two different data sets. You have the data before, you have the data after. So here I have small firm. I filter the before group in order to form a new data set. Let's run it. Then I create another one. I make it after. Let's run it. But here, unlike the situation whereby you are plotting the normal distribution curve on the two, because these are not separate, this is just one person, and this is just the same set of people, just the same, just one variable divided into two. So in this wise, what you are trying to do now is the difference. So you calculate the difference. In this case, I have the difference income after minus income before. So I get the difference. So it's I will plot the normal histogram for the difference. So that is exactly what I've tried to do here. Yeah. So this is what we are trying to look at. And in terms of the t-test. The t-test will be t.test. Go back to the original data set where you have the small firm. So we have small. Sorry, let me get the names. Small firm so that I'm not typing wrong variable names. Wrong. Okay, I have group income so that I don't mess up the. So now you see t.test income as a function of group data equals small underscore firm. Then paired equals to true. Fine. So in this wise, let me copy it to our PowerPoint to make it clearer. So let me stop sharing this. Let me come back, share the slide. So we're saying using this test for the difference in the income of small scale firms before and after COVID-19 lockdown, January. Sorry, let me share the screen again. Okay. So this is our interest now. So using small firm test for the difference in income of small scale farmers, small scale firms. After maybe starting after lockdown. So which means you can have before lockdown and after lockdown. Typical example. Yeah, so let's look at the t-scores. So in this case, we have the p-value is 20.883. That is the p-value is very, very small. P is 0.00000, far, far less than 0.05, which means the difference before and after was actually significant. So in which case, you do not reject the null hypothesis. Sorry, you reject the null hypothesis. So in which case, you are saying that the mean of the differences is actually substantial. The mean difference is calculated for you here, because that is the interest, that is the focus. Yeah. So let me stop sharing. so that look at ourselves. So that's the class for today. And I think it's very, very straightforward. Before I say any other thing, please, do we have some observations, some questions, or in the process of following me, you need some further clarification? Or maybe like your class rep used to say, we go back, go over it, practice it. Then if you have any question, then you post it to the WhatsApp group. Yeah. So what is your response? Class rep, let me hear you.
Yes, Prof. Hello, Prof.
Yeah, hello. Yeah, I can hear you.
Yes, Prof. I think if there are any questions, we may post in the WhatsApp group, because really during the lessons, it's not easy to follow, like do the practicals. We're only able to do it afterwards once you have sent the link, and we can just go through the video in your own pace. Then for any questions, I think we'll use the group platform.
Okay. Is she speaking the mind of everybody? I believe. So if you don't have any contrary opinion to that, then I think we can just assume and follow that. Now, yeah, we've made a lot of progress, but we still have to work on analysis of variance, correlation analysis, regression analysis. Those are the three things we need to do. And after that, we will now conclude the lectures on what is called power analysis. Yes, we have looked at all these one sample t-test, two sample t-test, paired. We look at analysis of variance, correlation, regression analysis. But how can we use them in order to determine our sample size when we are conducting a research? That's where we are going to end it. So again, we will go through all of them again when it comes to power analysis. That is where we are going to end the class. So we need about, just like I said before, I think class needs 3 lecture content. We've had 1, so remain just 2. So after 2, definitely we are going to conclude. I'm sure of that one. Because the next class, definitely we will go through correlation analysis, regression analysis, and the interpretation, and the computation, and every other thing whatsoever is needed, hypothesis, plus ANOVA. So those ANOVA, correlation, and regression is what we're going to do. Then the last class, we just run through the power analysis of everything together. So, and after that, then maybe we now decide on when you will do your final test. So I really appreciate what you are doing, because it's really helpful to me too, so that we conclude on time, so that you too, you will have adequate time to go through all these things and get ready for your exams. And maybe the last time we still have opportunity to do a thorough revision too, so that I can put you through some things that adventure you should prepare with respect to exam. But that will be after we have concluded the 2 classes. So thank you very much. I quite appreciate your coming and
Sorry, Prof.
your contribution. Yeah.
Sorry, Prof. So after this lecture, you still need 2 more sessions with us?
Sure. If you want us to conclude
No,
if you want us to finish the syllabus, or else I can just post it and ask you to go and read on your own to school.
No, we had already agreed on another session next week, Wednesday at
Oh,
1.
that's great.
Yes, yes. So I think we can have a slot for next week, Wednesday. Then we will see when we can. I think the next lecture we will be having a date for the next session again.
Okay, yeah, that's fine.
Yes.
So that's good. So I hope you try to practice the last one. Is there any question on that? Because you will have done that one anyway. Estimation of confidence interval, all sorts of things that you're supposed to have known now. I hope you are practicing the practicals. That's the most important thing. Yeah. Anyway, you still have opportunity to go through. And the best approach is make sure you download. You see, it's not easy just going to the internet, download everything, just download it so that you have it. So at your own time, you can go over and over, pause and listen, and so on and so forth. So I wish you all the best. Keep safe. God be with you. So I'm going to post this on the internet, then make sure you have it very, very soon. Yeah.
Thanks, Prof. Bye.
All right.